Okay, yeah, so the ontology of the many worlds theory. I said I will answer Tim's questions. I have to go forward rather quick, so it will be rather quick answers to all of that. And I will disobey, so I will use a configuration space word. I'll try to motivate that. So this is the outline. I will talk about configuration space, wave function, my proposed ontology, which is related to wave function realism, but a sort of a twist to it. And okay, and I will yes, I will propose I have this proposed ontology, and I will discuss how space-time state realism. But it's not really as good. So configuration space for n point particles, I call C of n. And so it's really the space of n points in 3 space. So that's sort of the mathematical definition of it. And I will point out that mathematical dimension is not equal to physical space dimension, which is, of course, obvious if you think of these points here in the figure, that there are point particles there. And they're obviously in 3 space. And they have many coordinates altogether. So the physical dimension is quite different from the physical space dimension, as Lewis and Lewis and Ney have discussed in the wave function collection edited by Ney and Albert. So, so it's clear that this configuration space is not equal to the 3n dimensional real space, just like 5 apples is not equal to 5. It matters what you count. The wave function gives a complex number for each element in C of n. And in order to make sense of that, to that to be of any physics, we have to say what it represents. And the wave function absolute squared is a distribution which gives the position of a system. So that means that the position is actually a distribution, somewhat of a revolutionary thing in a sense, but it's necessary, of course, in Everest quantum mechanics, because we only have the wave function, so there can only be distributed objects. If you expect to encounter, the reasonable thing is that you will expect to encounter situations where you find things with high presence. Presence is the word here for the local value of this distribution, rho of x. And so if you take that as a given, then you have a Born rule, as I've given in my paper. Physicists use this wave function precisely like that it's many points in 3 space. That's how things are calculated by physicists. And so, for example, in quantum mechanical scattering, we have this wave packet as function of time. And okay, I'm too close. Okay, so we have this wave function, and it has, of course, the coordinate of the projectile and of the target. And we get from that, physicists get a description from that, that the target, the projectile after scattering reaches the detector, and you can also have that the recoiling target reaches another detector. So it really describes what's happening in 3 space, and it works fine. There's no contradictions in that, so it actually works as a description of what happens in 3 space. A free atom or molecule, etc., any free object, the wave function factorizes into the center of mass and an intrinsic. And the center of mass part of the wave function will tell where the particle is located in the sense I described. And the intrinsic part will say how the components, the constituents are located with respect to the center of mass, as well as all other things like excitation energies, etc., everything we get out of quantum mechanics about it, a atom or molecule or whatever. And of course, we then have that we can think of macroscopic objects like this one, or a disk as I have there, that there are atoms located here precisely as the wave function tells. So that's how we will think of these microscopic objects being located somewhere and with atoms in them, which are described with the wave function, and all the bindings are described with the wave function, etc. And that seems to work fine. In a laboratory experiment that create world splittings, that won't change the dimensionality, but we have a very good description of it, that it splits the world, and decoherence is the process that defines this for all practical purposes as well. So we have separated classical 3D worlds. So now we can understand the bigger picture. First, just understand the world we have around us, and then understand there are world splittings. And so actually there were some splittings beforehand, which part of the wave functions, part of that we don't really see, but we suppose they're there. And this is much the way it is described, I think, with Lev the first day, and like Wallace also gave this sort of idea in the wave function collection. I don't have anything more. Sorry. Yeah. So the proposed ontology. First of all, a gauge change is a change of the vector potentials. And I have here index L on the vector potentials because I think of having different vector potential for different particle types. Also non-charged ones, by the way. And you can have all kinds of charges. I mean, you can have color charge, etc. And of course, a gauge change is a change of the vector potential such that the change is rotation-free. Then this will change the wave function, so that changes the phase locally in configuration space. And the gauge is physically relevant, so the ontology ought to be gauge invariant. And so, therefore, the gauge invariant properties of the wave function, that is, should be our ontology. And those are this density, which gives a position, a wave function absolute squared, and the current calculated in a gauge invariant way will also then be, of course, a gauge invariant thing. And the total spin state, which is sort of the array in spin, the total spin Hilbert space. And then, of course, things like masses and charges are gauge invariant, as well as electromagnetic and the electromagnetic fields, E and B fields. So that's the ontology. Now, Vaidman already 1999, or was it 1998, said that this density is the measure of existence. And that really points to an ontological character of this, if I understand the words correctly. In Q of t, of course, also the ontology will be the gauge invariance. That's easy to explain in QED, but QCD seemed to be a little bit more resistant to how that should be written down. It might not be so difficult, though. So we have in our Hamiltonians, in our or quantum field theories, local interactions, and that, of course, governs the structure of our world. Locality also singles out the positional basis as special. And so we shouldn't be surprised that the ontology has a spatial character. It's really to be understood. And we have no need and no ability to interpret quantum mechanics for a general Hamiltonian. We have no idea how that would work. And there's no reason to think that the ontology should be similar if you say you have a different Hamiltonian, a non-local one, for example. It's nonsense to think about, I think. And then some words against Hilbert vector ontology, because basis states will vary with gauge what they mean physically. So that will be a problem for that. And to my mind, the change of Hilbert space base is simply a mathematical transform that is good for calculations, but shouldn't be viewed as anything more than that. Well, it can be helpful also in some understanding, but still. Just like Fourier transform of sound, it helps you to understand sound, because you can get the sort of what kind of spectra it has in frequencies. And the abstract Hilbert space is void of physics, just like natural numbers are void of oranges. So then some presentation of Wallace and Timpson's suggested space-time state realism. And their motivation was the refusal of wavefunction realism, because they argue that the domain there is simply this 3n dimensional real space, which I think is a misunderstanding. And they argued also that Albert's narratability problem was a problem, which I think is not a problem. Possibly I get time to discuss that later on. So that proposal was to divide the world into subspaces, subsystems consisting of 3 space regions and what is in there. And then, of course, you have that the state is a reduced matrix element you get by tracing out the outside. In QFT case, quantum field theory case, the state is given by the operators that are localized in the region and their algebra. And they mentioned that themselves that the pro here is the ontology is clearly related to space-time, which is good for relativity. But and they also themselves mentioned that the drawback to this ontology is that it's not really complete, it's not really narratable, because the density matrices of 2 regions don't contain the information enough to construct the density matrix of a combined region. So they do acknowledge that as a drawback. And to further give some criticism towards space-time realism, I would say that space-time realism, they divide, well, rather their arguments for it, they divide a Hilbert space into local regions. But when they say they can do that, actually implies that there is an understanding of the wave function in 3 space. So their initial statement that there isn't is sort of very strange. And they also noticed, the authors also noticed that quantum field theory imply that the non-relativistic wave function domain is the one I've advocated here, C of n, the classical point particle configuration space. But the possible, but they still didn't recognize the possible wave function realism in spite of that. Their QFT discussion relies either on that there is a QFT state being a real thing, or it seems to be they have as an alternative a total abstraction, which seems void of physics. So either you have a wave function which is real, or you don't really have anything. So all that they have achieved is loss of coherence between regions, hiding entanglements between regions, and therefore also in some sense hiding world splittings. They also claim to get a set of macroscopic worlds, but I find the argument for that weak, so I'm not really convinced that they actually can get that either. And every aspect that can be described with space-time state realism can also be described with the gauge invariant ontology that I've given you, but without the drawbacks. Because of course you can still look at a single region. I mean, if you would like to look at locality questions that has been discussed, then of course you can just take a region and take the density matrix that describes that. That's fine, that goes within this, no problem. How many minutes? It's finished. Okay, so I'm finished I'm finished.
I'm slightly puzzled to hear you describe Chris and me as criticizing wave function realism on the grounds that it's in R3n. I mean, we're at pains to defend the metaphysical coherence of wave function realism. Our problem with wave function realism is that we don't think it works in the quantum field theory context. So the question is, you want to say everything that's done in wave function realism can be done just as well in, everything that's done in the space-time state realism can be done just as well in this framework. What does this framework look like for an interacting quantum field theory?
Well, very much the same. I mean, in quantum field theory, if you would like that to give us the, say, non-relativistic, so take non-relativistic there.
No, I want full relativistic interacting quantum field theory, particle number not conserved.
So, then you have creation operators. Actually, I had a slide there, but sort of lost the connection. I have it here. So here, say in second quantized, or for that matter, Q of t, n particle state is creation operators at different points in space, in 3 space, amplitudes at the different in configuration space then points, and then integral over that. That would be the wave function, say, in second quantized, which is very much the quantum field theory, and which is precisely the kind of wave function. I mean, I've been working in many-body quantum physics, making calculations, and we have never seen any difference between the second quantized, that's just a bookkeeping. It gives exactly the same wave function, exactly the same physics that we work with without that. And also then in quantum field theory, this will be the construction. there you will normally have sandwiched this thing here, and then multiply with that annihilation operators, and then the vacuum.
Sure. So I mean, in a solid state use of quantum field theory, I can see that's fine. But in that situation, you've always got a background particle description, and you can think of the QFT structure as just a convenience. But if I'm looking at a relativistic field theory, the particle structure is not fundamental in the theory there. Particles are turning up as excitations of the fields. The right particle spectrum is, I mean, you can contest these things, but they're at least standards in the QFT literature. And
well,
the particle breakdown is energy dependent.
But you're not really right there about the literature. Because, I mean, the fermions are really being there. Though I might be slightly old-fashioned with respect to quantum field theory, that I like to use J-Rex-C. And of course, Bogoliubov sort of made away with that, which is nice in a sense, because when you have the C, you sort of have like particles are more fundamental than the antiparticles, and the Bogoliubov got rid of that. But you can do it in in several different ways in quantum field theory. In quantum field theory, you still have a configuration space, but it's sort of C infinity, whatever way you do it. I mean, you can have some, say, at local positions, a spin variable that corresponds to how much you have a particle there, and one spin variable with respect to how much an antiparticle you have there, and so on. So combinations of that at each point is fine. And the electromagnetic field, yeah, well, there is just a new variable at each point, which is, so you have just, as I say, a C infinity, because at each point you have sort of a dimension. And so that's it.
So, I mean,
I don't see a problem.
Okay, so I'm skeptical about the viability of that in modern relativistic QFT, but that would be a long conversation. Let me just circle back to the point that our reasons for space-time-state realism are all about the fact that we're skeptical about translating this to mainstream QFT. It's nothing to do with the conceptual
okay, then I misunderstood you somewhat, because also, as I said, it didn't really make full sense. So then we agree.
Hi, so thank you for your talk. I'm wondering about your ontological proposal here, thinking of Cn and C infinity. So in the case of Cn, it seems like your proposal is thinking of the ontology of the wave function as an assignment of properties to every endpoint in ordinary space.
Let's see. Can I get that here?
Is that a good way to think about your proposal here?
Yeah, okay. So what did you say? That this is not in ordinary space, but in configuration space. So it's with respect to several points in 3 space. It's a function of several points in 3 space.
I see. So what is the proposed ontology here again? Could you just clarify?
It's what it says there. It's the wave function absolute squared, which is the gauge invariant. And the current calculated in a gauge invariant way. So it's very much the same thing that goes into Bohmian physics, which I find nice. That means that they have sort of caught on the right quantities. It's the total spin state. So spin of all the particles and how they're coupled. You get how the spins are coupled. You get an array in that Hilbert space. And the masses and the charges. And the electromagnetic fields, if you only think about QED or so. That world of the only interactions are electromagnetic. So otherwise, you, of course, have the others.
So they live in the high-dimensional configuration space, right? They are defined on the high-dimensional space.
Well, in the sense I already started with, that this is a space which is, the physical space is 3-dimensional. So don't try this one that is high dimensional and therefore weird. Yes, it's weird because it's quantum mechanics. I mean, the first time I encountered the wave function of, as a function of many positions in space, one get completely awed. Can one actually deal with a thing like that? But what I say is that in practice, it's proven by physicists. Yes, we can deal with that. Yes, we can describe the physics in 3 space with it. Period.
I see. So
You have to prove me that that fails in order to get a point that it fails. Period.
All right, Don Page. On this slide where you had these creation operators, I don't know. We should flash it back up again. Anyway, the point was it seemed like you, aside they're local, but I think creation operators are generally non-local, aren't they? I mean, each creation operator, you have to integrate it over.
Where did I have that? No, it's not.
It was, yeah, let's see, it was what you showed a bit ago. You were talking about, we were talking about quantum field theory, and you were saying, okay, you had a,
I went the wrong way.
anyway, it was, yeah, there,
Yeah.
there we go. Okay, so you have these size, these various size, which are supposed to be creation operators, and
Yeah,
but
I
the
mean,
creation operators are, I mean, okay, you can create a particle in a mode, but then you have to, it's got an integral of that mode over the 3 space.
Well, no,
So
I mean,
you
you
don't
can have, I mean, if you look at how Bjork and Drell or something, the canonical quantization, you certainly work with operators that are local in space.
Yeah, but they're not I mean, the field operators are local in space, but then you have to do Fourier, well, if you want to do
But
energy
then,
momentum modes, do
then
Fourier.
you can transfer that, but I mean, the starting point is really in 3-dimensional space. And then
Right, but I don't think
you go
you
from
have,
that
okay, I'm
to
not
say,
that much an expert, but I don't think you
for-
can have the creation operators themselves are always non-local. I mean, if you made it absolutely local, you'd get infinite energy because you'd have infinitely high frequency.
Yeah, but
you'd
you
have a delta
but-
function.
But then I have here an integral over, so of course I don't stay there.
Sorry?
I have here an integral over space.
Right, but you don't have I don't see any mode.
Not
Well,
particular mode, but still. So it's not really in the end localized.
Yeah,
Still,
I think
it's
somebody
sort
that's
of
a better expert in this than I, but I just
still-
thought,
still-
I thought you can't, it was just under the impression that creation operators are never local. You can't write them in this form, but maybe in
No,
somebody
you
that's a better
can.
expert at this.
You can, and you do that sort of, say, in lattice QCD and so on. And it has its problems in relativistic theory. The Dirac one, you can only localize if you take the mass to be infinite.
Yeah, okay.